Find the value of x, which minimizes the function f of x, where x is between 1 and 2. In this problem, a function f of x is provided, where the cosine term reads in radians. When searching within the range from x equals 1 to x equals 2, we notice a local minimum exists closest to either 1.7, 1.8, 1.9, or 2.0. Also note that the figure is not drawn with enough accuracy to determine the correct answer by observation. The golden section search method locates a function minimizer x over a closed interval 1 to 2, assuming the function is unimodal over that interval. Unimodal means that the function has only one local minimum over the given range, from 1 to 2. We'll focus in on the range from x equals 1 to x equals 2, where the dashed line is only an approximation of the function f of x. For the golden section search method, we'll assign variables a0 and b0 to be the minimum and maximum values of the range that contains x. Then, we'll evaluate f of a0 and f of b0 by plugging in 1 and 2 into our function f of x, and we get 3.161 and 2.335. Next, we'll define two new values on the x-axis, a1 and b1, which we will calculate using the functions for a n plus 1 and b n plus 1. For this case, we'll substitute in n equals 0. We'll also substitute in 1 for a0 and 2 for b0. Lastly, the problem states to use 0.382 for rho. Because rho is approximately the inverse of the golden ratio minus 1. This makes a1 and b1 equal to 1.382 and 1.618, respectively. Next, we'll compute the values of the function f of x using 1.382 and 1.618 for x, and we calculate 2.661 and 2.429. Since the function f of x is unimodal, we know the minimum value does not fall between 1 and 1.382. The minimum must be between 1.382 and 2. We have just completed one iteration of the golden section search algorithm, which reduced our range of possible values of x by a factor of 1 minus rho, or by a factor of the golden ratio minus 1. Since our four possible answers all fall within the range of 1.382 to 2, then we'll perform a second iteration of the golden search method, and we'll continue with as many iterations as necessary until our range of x values only includes one of the four possible solutions. To begin the second iteration, we'll first adjust the range of the graph to include values from x equals 1.382 to x equals 2. Next, we'll assign a1 to be 1.382 as it was before, and we'll set b1 to equal the upper bound, 2. Next, we'll find x values for a2 and b2 using the same equation as before, but this time assigning n to equal 1, which means we'll plug in the values for a1 and b1. And as in the previous iteration, rho equals 0.382. Therefore, a2 and b2 calculate out to 1.618 and 1.764. If we plug these values into our equation f of x, we compute f of a2 equals 2.429, and f of b2 equals 2.344. Since f of b2 is smaller than f of a2, then we know the value of x, which minimizes f of x, does not fall within the range from 1.382 to 1.618, but rather between 1.618 and 2. So we'll continue with a third iteration. But before we do, I'll point out that one advantage of the golden section search is that our value of a2 and f of a2 in the second iteration are the same values as b1 and f of b1 from the first iteration, before we assign b1 to equal 2, which occurred at the beginning of the second iteration. Moving on to the third iteration, we'll refocus the plot from x equals 1.618 to x equals 2, and compute the values for a3 and b3, which equal 1.764 and 1.854, respectively. After plugging these values into our function, we have 2.344 and 2.320. After reducing our range again, and assigning a3 to 1.764 and b3 to 2, we notice the value x equals 1.7 is no longer a candidate as a solution, because it falls outside our range of values. Next, we'll compute a4 and b4, which equal 1.854 and 1.910, respectively. The value of f of a4 equals 2.320, and the value of f of b4 equals 2.317. Now, since the range is between x equals 1.854 and 2, we know our answer for x does not equal 1.8 either, because it is outside the computed range. a5 and b5 equal 1.910 and 1.944, which makes f of a5 equal to 2.317 and f of b5 equal to 2.321. Since f of a5 is less than f of b5, the range for x is now between 1.854 and 1.944. Looking back at our possible solutions, the answer is C.